So we have Zach, Bing, Thomas, and me to present to you guys polarized neutron scattering measurements of magnesium oxide using HighSpec. Okay. Just a information slide for you guys for those of y'all who don't know about magnesium oxide. Magnesium oxide is an antiferromagnet, magnetic order below 118 K. Above there, we have a cubic glass for the magnesium oxide. Along the 111, perpendicular to that plane anyways, you have the ferromagnetic ordering, and planes that are parallel to said plane, you have the anti-parallel ordering, okay? And by using HighSpec, polarized neutron elastic scattering, we're able to determine that magnesium oxide is indeed a antiferromagnet. Okay, so the next question is, what is HighSpec? HighSpec is short for hybrid spectrometer. So that is our lovely beast of a machine there. We have on the left side the detector that is about 60 degrees angle. Moving forward, you see our super mirror collimator, sample space right in the middle, spin flipper, and a vertical collimator. Okay, this guy just used his here at SNS, so he uses the high flux pulse neutron for the inelastic scattering and uses the time of flight for resolution. Okay, so you might be wondering then, all right, so that's the equipment. What good is this beamline for? So you can do lattice and magnetic dynamics in functional materials, excitations in geometrically frustrated magnets, ground states, and quantum magnets, quantum critical phenomena, and more. So for example, just a couple of I stole a couple of pictures from some papers that the research group here has published recently. You can look at iron telluride compounds on the top right there. You can see spins collimated in a single column on the left. So that'd be figure A. And then you can investigate the said crystal under different parameters, and they can see bicollineated columns, so that'd be figure B. And then the figure below, you can see again a different iron telluride compound. The figure A there is at 8 degrees Kelvin. You can look at the inelastic scattering, Bragg peaks, and then compare that to maybe a low temperature scale, for example, figure B on the bottom there at 5K. All right, they've noticed that they could see more or Bragg peaks than they did originally, and so you can investigate further using polarized neutrons to determine what could be affecting those or what could be causing those Bragg peaks. Okay, in this case, they shot a polarized neutrons at the sample, and they could see. Okay. They could see no change in the Bragg peaks, indicating that this sample is probably non-magnetic. Okay, and so to give a further description of our HighSpec machine, I'll leave it to Thomas.
So here you see a diagram with the various components of HighSpec. So we have an unpolarized incident beam of neutrons, which hits a Fermi chopper, which sets the incident energy and provides energy resolution, which is about 2 to 20% from the online website. After that, it hits a monochromator, Heusler crystal, which only Bragg reflects spin-down neutrons. So the name hybrid HighSpec comes from hybrid spectrometer. So it's a cross of a time-of-flight spectrometer with a triple axis. So after it hits the monochromator, there's an optional spin flipper, which we need to use, as you'll see later. And that could basically flip the spin down to spin up. Around the sample, there is various magnetic coils, which we could use to control the polarization of the incoming neutron beam. The neutrons scatter off the sample, and they go into an analyzer, which is a supermirror. And the supermirror only reflects spin up. So HighSpec is a cold uses cold neutrons, so there's a cryogenic H2 moderator. The Fermi chopper selects the incident energy, and it provides the energy resolution. The monochromator that we used is a Heusler crystal, which only Bragg reflect spin-down neutrons. And because of this, half of the intensity is lost. You can't really see it, but if you wanted to do unpolarized measurements, you could use a pyrolytic graphite array, which doesn't have this problem. So a Mezzai flipper is used to flip the spins. So it basically sets zero magnetic field inside the middle region, zero vertical magnetic field inside the middle region, but there's a horizontal field which rotates the spin. And the polarization around of the incoming neutron beam is controlled with magnetic coils around the sample. And finally, the analyzer is a super mirror, which can only reflect spin up neutrons.
So I guess what we're all asking ourselves is, why would you want to commission such a really complicated and specialized piece of equipment? And there are a lot of benefits. Primarily, so it has this humongous swath of reciprocal space that it's accessing, 60 degrees and 2 theta. It has really fine energy selection and also resolution using a monochromator and time of flight, respectively. The spin polarization is really what sets it apart from a lot of the other spectrometers at Oak Ridge. And there are just so many applications. You can change out the sample environments and whatnot. So I think after this talk, or at least maybe even now, you'll notice that HighSpec really is the best for a very limited number of experiments. So with that in mind, I'll highlight the really relevant aspects of polarized neutron spectroscopy, and I promise it'll be relatively painless. So let's consider a general case where we have an incoming beam polarized with the polarization along some orthogonal axis, x, y, or z. And we're going to be striking a sample that is magnetically ordered somehow. And it has nuclear structure factors, which we'll call N, and magnetic structure factors that you'll remember you can only access ones that are transverse to the to Q. And Mendeyev and Bloom in the 60s came up with these equations which capture most of the relevant physics in magnets. So you'll notice in the first equation in blue, we have for a non-spin flip channel where the polarization after scattering remains the same spin direction. There's a nuclear component, there's a transverse magnetic component, and there's also an incoherent segment of that. And if it spin flips, which is to say it goes from spin up to spin down or vice versa, it looks like that. So we'll consider a pretty simple case of a powder with no incoherent scattering, just for the sake of argument, and we'll set we'll make it isotropic, so all the moments are the same along all the axes, and friendly reminder that if you're considering, if your Q is along X, then the M perpendicular X terms will go to 0. And also, if it's isotropic, then there will just be 2m squared in the bottom equation. So directly from this, you can see completely separately contributions from phonons and magnons. And I'll remind you that these n's and m's represent the structure factor, which is a function of Q and energy. So you're getting all of the phonon and all of the magnon contributions from this, which is really powerful to condensed matter physicists. With a small stipulation that there's actually a heck of a lot more to correct for with HighSpec in order to get beautiful publishable data. So with that, I'll leave the specifics of the analysis to Bing.
Okay, so now we all know what the theory looks like. Let's take a look at the data. So before we do the experiment, we need to run some simulation. And here what I did is we ran this full prof, and here we focus on this nuclear 111 peak just to make sure that we can actually see some signal in our detector. And here we have to use this 6-point method, which is called XYZ polarization analysis. So So 3 times 2 equals to 6, and the 3 corresponds to the polarization. We can polarize the neutron parallel to x direction, y direction, or z direction. And here x is defined in the q direction with the momentum transfer direction. And 2 here corresponds to 2 spin configurations, which means you have the spin flipped, or you can have the spin non-flipped, which means up, generated and up detected, or down generated, down detected. Both of them are non-spin flip. Okay, so here are the 6 measurements we did, and we can see there's lots of stuff going on here. We can see the nuclear peaks here at those positions, and let's take a closer look at this one here. And this is a cut from the previous picture that I pointed, and we can see we indeed have this nuclear 111 peak here as we expected, and we also see something here and something here, which looks like they might be magnetic peaks, which are fantastic. But if you take a closer look at other cuts, and you can find out according to the theory, here the red curve should be twice as intense as the black curve, and you can see here. 2 minutes. Okay, you can see here there's a glitch, and it turns out this is because the spin flipper doesn't work 100%, and sometimes it lets spin pass on without being flipped. So we also have to correct something because of this geometry of this, and this is called sharp angle, and to correct this, you need to use this equation, but fortunately, those are all already taken care of by this amended script. All you need to do is put in your random numbers, and voila. You can have your nuclear peaks here and your magnetic peaks well separated. You see nuclear signal, magnetic signal here, and this blue curve is your nuclear peak. And we can also estimate something which is the spin, incoherent nuclear spin scattering intensity. So now, if you focus on your magnetic signals, you can see here, we can observe this AFM spin, that's antiferromagnetic spin wave in magnesium oxide, and there are some features washed out because of this the powder sample. And you can compare your experiment with some simulation. This is provided by Obi, the beamline scientist. This is the simulation using spin W. And with this beautiful picture concludes our presentation about HighSpec. Thank you. Questions?
For this experiment, you used a single crystal, correct?
No, we used magnesium oxide powder, yeah.
What's the difference between using a powdered sample and a single crystal in this case?
Well, I think in this case, we only took data for 4 minutes per configuration. Using powder, you have the average. I think it's just to have more signal. If you use single crystal, then it's going to be more difficult to observe the peak. It may take longer. That's
Are there other questions? Do you know where the original experiment was done to determine the antiferromagnetic structure of manganese oxide?
I know this is done by Cliff Shaw, and he won the Nobel Prize. I think it's here.
It was done at the graphite reactor.
Oh, cool. Yeah. Okay. So any other questions?
Yeah, but the original work was done by Shaw and at the graphite reactor. No other questions? I guess it was perfectly clear.
Okay. That's our purpose here. Thank you very much.